So that sort of recaps basically our whole chapter, that we had kinetic energy, we had work, and then we also have this work energy theorem where if I do work, I change the energy of an object. And we'll see that more later, and we'll do some integral calculus regarding that. Now let's also look at the conservation of energy. Conservation of energy just says that when dealing with conservative forces, when conservative forces are at play, the initial energy equals the final energy in a system. So for example, or to write this in equation form, we would say that EI is equal to EF. Our initial energy is equal to our final energy. Only when conservative forces are at play. So we're really only dealing with two forces, our kinetic energy and our gravitational potential energy. We're only going to have the force due to gravity at work. We'll also see later, we'll incorporate friction into this, but remember friction isn't a conservative force. Friction will actually take away energy. We'll see how that affects a system, how it can actually cause a system to lose energy. And so we'll use the conservation of energy in a sense, but we'll add in this non-conservative force. So thinking about a system that only has two types of energy, gravitational potential energy and kinetic energy, we would rewrite this as UI plus Ki equals UF plus Kf. In a system, the sum of the potential and the kinetic energy will always be constant. It will always, at the initial point, be equal to the energy at the final point. Let's work through an example, and you'll have one similar to this, and there's one like this in the homework. Let's say that I have an object. It has a mass of 100 kilograms, and it has an initial speed at this point equal to 10 meters per second. When we talk about initial and final, uh, that's a little bit misleading because really when we talk about initial and final, we're talking about two different points in the system. So this object, for example, is going to move up, it'll move down, and then it'll move back up again. We're going to be comparing one position, right here, for example, to another position, right here. So in one part of the problem, we'll take this to be our final position. In another, we'll take this to be our final position, and then in another part, we'll take this to be our final position. So don't think of our initial and final positions as fixed points. In fact, if you want to think about it a little bit differently, you could say that uh, E1 is equal to E2. That is that the energy at one point of the system is going to be the same as the energy at another point. Initial, final, 1, 2, it doesn't really matter how you think of it, but the point is that the total amount of energy in that system that is contained by this object is going to be constant throughout. Let's say it has 10 joules here. It's going to have 10 joules here. It'll have 10 joules here. It'll have 10 joules here. And it'll also have 10 joules here. That total energy doesn't change throughout the entire system. So a couple of things we know too. It says that at height h, the particle comes to rest. That is that V equals to 0 over here. I'll call this VI, and I'll call this VF at this point. Also notice that over here, H is equal to 0, and over at this point, H is equal to, well, I don't know what it's equal to. I want to figure out what that height is. Okay, so now once you identify your initial and your final positions, or your first and second positions, I'll take this as my initial. I'm taking this as my initial because I know the most information about this. I know its y position, and I know its velocity. And this is going to be my final position. I'm taking this because I want to know what h is. That's what the problem is asking. What is the height h? And then I think about the energies. Now, both points in the system can have one of either u or e, u or e, or both. Both points in the system can have either the kinetic or the potential energy. So the first point, what does it have? Kinetic, potential, or both? Remember, U is equal to mgh. E is equal to 1 half mv squared. So the first point, this initial point, does it have U, potential energy, E, or I'm sorry, that should be K. K, kinetic energy, or both? It only has kinetic because H is equal to 0. Let's change that E to a K. And then over here, does it have U or K or both? It only has U because the V is equal to 0, and since kinetic energy is 1 half mv squared, that is equal to 0. So here I get this is equal to 0, and this is equal to mgh. Here, this is equal to 0, and this is equal to 1 half mv squared. So we can write that as an equation. We'll say that U initial plus K initial equals to U final plus K final. All right, so this is going to be 0 plus 1 half mv squared. I'll call this VI just for kicks, although, again, we're not thinking of it as an initial position, but just some point in the system is equal to, or excuse me, equals mgh plus 0, because the kinetic energy at the final point is equal to 0. Now we have this. I can solve this for h. I can say 1 half. Well, before I do that, let's notice that my masses here cancel. I can divide through both sides by m, and so my 1 half mv squared will just become 1 half v squared. You'll follow there what my masses cancel out? You'll find that in these conservation of energy problems that the mass will always cancel out. I can divide through by the mass. So it's going to be 1 half of VI squared. That's 1 half of 10 meters per second squared is equal to, remember the mass cancels, so I'm going to leave it out, 10 meters per second squared. That's G times H. And then I solve this for H. So this is 50, half of 100, divided by 10 is equal to H, which is 5 meters. All right. So what I've done there is I found the height h, that this roller coaster or this object on a wire, it comes up and then it comes back down and then it stops when it reaches a height of 5 meters. All right. Now I can also find the velocity at different points. So let's think about this. We're gonna, for part B, we're gonna find out what is the velocity here. Is the velocity gonna equal to 0 at this point? Y'all been on a roller coaster? Yes, no? Yeah. So on a roller coaster, you go fastest on the low hills, right? Because you go up to those really tall hills, usually the tallest hill is the very first one, uses the chain to pull you up. You go up to the tallest hill, that's when you're gaining all the gravitational potential energy that will take you through the rest of the system. Now, the thing with a roller coaster is it's not all conservative forces. You have frictional forces acting. And so you have to have several points during the roller coaster where you have a chain that pulls you back up and gives you more energy. But the same idea occurs here. The faster you go will occur at the lowest points. So here, over here, my velocity was 0, but over here is not going to be 0. And then the fastest point will be right here, where I'm at the lowest height. All right, so let's figure out what is the velocity at h over 2. Now that we know h, we know that this height is equal to 2.5 meters. And I want to know what is the speed at that point. I'm going to go down to the next page. What is v at h over 2? I'll redraw the figure. It sort of looked like this. This was 2.5 meters. And I want to know what is the speed here. Well, begin just like we did before. Ui plus ki equals uf plus kf. Well, we're taking this as our initial position, and this is our final position. So we had some things cancel out. We said that this was equal to 0 initially. So I have 1 half m times v initial squared. That was at 10 meters per second. Equals to m times g. I'm going to go ahead and put in the value for our height here. 2.5 meters plus 1/2 mv squared. Notice my m's all cancel. M cancels there, there, and there. I just divide through by m on both sides and it gets rid of those. And then I can solve for, well, I'm looking for VF here. So take just a moment and solve that for VF. I'll give you a minute and then I'll catch up with you. If you finish that, think about what is the speed at point C. How can you calculate that, or how can you just reason out what that speed should be? Keep working as you are, but let me just go back through this. I want to know the velocity here. So I say the total energy here equals to the total energy here. At this point, I only have kinetic energy. At this point, because it's both has a height and it's moving, it has potential because h is not 0, and it has kinetic because v is not 0. And so now I set this up, 1/2 mvi squared, canceling out my m. That gives me half of 100, which is 50, equals 10 times 2.5, that's 25, plus 1/2 VF squared. Do I get a value? Ish. No? What's that algebra? Huh? Yeah, it's about 7 or so. Go back and check your algebra. But if you have it set up like this, as usual on your test, if you have it set up right, if you make just a small error like that, I'm counting for points is all. So here I subtract 25 from both sides. So I get 1/2 VF squared. Why is it 50? Because our initial speed here is 10. And so 1/2 of 10 squared. 10 squared is 100, and a half of that is 50. Josh, I think I know what you did. I think that here you took half of this, and then you took the square root. When really you want to multiply both sides by 2. That gets rid of the half. I'm pretty sure that's what you did. All right, so I multiply both sides by 2. And Nicole, did that answer your question? Nicole? Yeah, I did skip a step there. Let me show you. I'll write it in here. I said 1/2 of 10 meters per second. That's my initial speed. This value is squared. Should have had that on the previous step too. Yeah, see, it was 1/2 of 10 meters per second squared, and then that becomes 50 because half of 10 squared is 50. And then you divide that by 10. All right, so this becomes 50 equals VF squared. Take the square root of both sides. The square root of 50 is about 7. 7 times 7 is 49, so it's equal to 7 meters per second. All right. Now, if I want to know the speed at point C, I could go through this whole thing again. I could set up our business where I have UI plus KI equals UF plus KF. But you would find that at the initial point, like it was here, the potential energy is equal to 0. What about at point C? I'm sorry, it doesn't say what point C is, does it? Point C is right here. At the lowest point, it goes up, and then it comes back down, and then it goes all the way up. So what is the speed at point C? speed at point C? It's going to be 10 meters per second because if I write out my conservation of energy, I have Ui plus UF, or excuse me, KF, Ui plus KI equals UF plus KF, right? Initially, Ui is 0. In the final state, Ui is also 0 because I'm looking at this point and at this point. And on both of those points, H is equal to 0. And then I just have Ki equals Kf. If the total amount of energy is in kinetic energy, and they both have the same kinetic energy, and they both have the same mass, then that means they're both going to have the same speed as well. I tell y'all, we went on a roller coaster over the summer. I tell you about this. We went to Six Flags in St. Louis over the summer, and my wife, who really loves roller coasters, I give her take a roller coaster, but my wife really likes roller coasters. She wanted to go hit some of the roller coasters at Six Flags, and they have some pretty good roller coasters there. But our kids are 8 and 11. They weren't really sure, and I wouldn't say they're timid, but they're kids. They're not always real brave to do stuff like that. So we thought we'll just get into Six Flags and just head straight to the roller coasters, and we'll be all excited about it. And that way they'll just sort of get caught up in the moment, and they'll just go on the roller coaster. And they did. Like we hit the gate. We were the first ones in the gate. We ran back to the roller coasters, and we were the first people on, and we were the only people on the roller coaster. And they were all excited, and they locked us down, and we started going. And then they like freaked out, like, no, I don't want to do this. I want to get off. And like, sorry, we can't get off. And then we couldn't get them on another roller coaster the entire day. Later in the day, we got on we didn't call it a roller coaster. We said, oh, let's go on the train. It was because it looked sort of like a train, but it was a much tamer roller coaster. Um, but anyway, so you will have a roller coaster problem on the test, and you have one like it in your homework. You have one like it in previous exams too. Make sure that you can do it. It'll look very similar to this. We'll do another example for you to try it out. All right, let's try this. Brennan, you want to come up? Just sit right here. So this is a bowling ball. It's a pendulum. You ever seen this before in physics or whatever? So this, I'm going to hold this back here like this, and then I'll let it go, and then we'll see how the energy converts from gravitational potential energy to kinetic energy, and then it'll come up, and it'll convert all to gravitational. Is that right? Is that how it works? Are you ready? No, that's not how it works, because it'll bust them in the face. All right, here, Brennan, hold that. All right, so hold it right up next to your chin. All right, so right now all the energy is in gravitational potential energy, right? And as he lets it go, as it gets to the bottom, that energy will go to kinetic energy, all kinetic energy. That'll be its fastest point. And then it'll come back up over here, and all that energy will go back to gravitational energy, coming back, and it should go, it'll lose a little bit of energy, you'll see, because it won't come all the way back to his chin, but it'll come very close to his chin. All right? You want to try it? Now, don't move and don't give it a push, because if you push it, that gives it extra energy, and it'll come back higher than where it left off, which would be bad for you. Okay, go ahead. You did flinch just a little bit. So it's never going to, you can go back to your seat. It's never going to go back to a point that's higher, as long as you don't give it initial kinetic energy. Let's see, this is a little loop-de-loop. The thing that we went on did not, the roller coaster, I mean, it didn't have a loop-de-loop. We couldn't really get them to do that. But I have a couple balls here. One is a small one, and then one is a big one. I can put the small one here. You think it'll have enough energy if I put it right here to go all the way around the loop? I'll hold it up so y'all can see. Of course not, right? It just sort of goes a little ways, but it doesn't really go all the way. Look, if I put it up here, it goes all the way through the loop. Now, what about the big ball? Do you think that it'll do any better or worse? Does changing the mass of your object affect the way that the energy translates between one another? Let's think about it. Let's look at the mathematical formula that we had. Let's go back up here. When we write the conservation of energy, Notice that when we write this, that our masses, they will always cancel out. So it doesn't matter with your big ball or your small ball, it's still going to have the same speed throughout the entire system. Now, as we'll see later, if you have a bigger ball, you'll have larger frictional forces, and that'll actually cause it to slow down than to go faster. Let's try this. It does the same. All right? That's pretty cool, no? We can look at this later. Um, let's work through another problem that'll be similar, and it's a problem that we've worked before, actually, but we worked it from a kinematics perspective, and now we're going to work it from an energy perspective, and you'll find that it's a lot easier. And the problem will be I'll take something, I'll throw it up into the air, and then it'll come back down into my hands. We've worked that problem, right, where you have to do, gosh, how do you do that? Well, you say, well, the velocity at the top goes to 0, and then I use that to find the time. Is ringing a bell for y'all? Find the time. I can figure out, okay, what is the speed at the various points. So there are things that I can do to work this problem, but we'll see that with energy it's a lot easier. Let's watch this video. This video went viral, I don't know, a number of years ago. I like it because the music is really good. I'm sorry, hold on. There's a lot of folks online that say it is true, and then a lot that says it's not true. But anyway, it makes for a good energy problem. It makes for a good kinematics problem. Like I said, one that we've worked before. Something that throw it up in the air and it comes back down. But a lot easier to work from the perspective of energy to sort of draw what we have here. Here's my basketball goal. There's the young lady that they threw up in the air. We really just need to know the height and a couple other things that we can make some assumptions about. First of all, a basketball goal, it's how high? 10 feet, right? Is that right? Yeah, so about 3 meters. So I'll call that 3 meters. Maybe a little more. And then let's say that she goes another 3 meters up above that. So we'll say that her total height, which I think is from the video is about right, is that she goes to a maximum of about 6 meters. Um, in the first part, we need to know the woman's total energy. In order to know the total amount of energy, we'll need to know her mass. I know that I've said that the mass cancels out, but that's because we've never been asked what is the actual energy. So in order to figure out the actual energy, we'll need to know what is her mass. She's pretty tiny. What do you think her mass is in kilograms? Y'all remember what sort of a typical person is in kilograms? Or how about in newtons? What's the typical weight in newtons? About 700 newtons. And that's how many kilograms? How many kilograms is 700 newtons? 70. It's just a factor of 10, right? For G. So let's say she's quite a bit less than an average person. Let's say that she's about 50 kilograms. That's her mass. All right, so I want to know what is her total energy at the top of her trajectory. And then I also want to know what is her speed in part 2 at the bottom of her trajectory. And then in part 3, I want to know what is her speed at this point. I'll call this V2. I'll call this V3. And then her total energy at the top, we'll just call that E. So her energy at the top of the trajectory is equal to her potential energy plus her kinetic energy. But I know one of these goes to 0. At the top of her trajectory, which of these goes to 0, U or K? K, because her speed goes to 0, right? So K goes to 0. And I'm just left with M times G times H. I know all this. That's 50 kilograms times 10 meters per second squared times H, which was 3 meters. Excuse me, 6 meters. So that's 500 times 6. That's 3,000 joules. All right. Go ahead and try part 2. You want to know the velocity or speed at the bottom of her trajectory right after she leaves the guy's hand. So what is V2 at this point? You want to think about what is the energy you about a minute, and then I'll step in. So go ahead and try this on your own. What is her velocity at the bottom of her trajectory right after she leaves the guy's hand? It looks something like this. U1 at the top is mgh. At the top, I know the kinetic energy goes to 0. At the bottom, the potential energy is 0. So the total energy is 1 half mv squared. I know our mass, but I don't need to know it, so I'll just go ahead and cancel it out. And I'm solving now for v, which is the square root of 2gh, um, which is the square root of 2 times 10 times her height, which was 6. That's the square root of 120, which is approximately 11, I think. 11 squared is 121. Is that right? Y'all get 11? All right. By the way, I know that you guys, and I like to do it too, I know that you like to put in numbers at a stage like this, but it's often better for you to write it like this because sometimes when we put in numbers, like I said, I do it too, I understand that. But sometimes when we put in numbers, we'll make a mistake in how we put in the numbers and how we calculate it. And if you wait until this step to put in the values for your variables, you can sometimes circumvent those mistakes or prevent them because you can go back and check your algebra more readily if you write the expression first and then put in the values for your unknown. Um, but, whatever you choose to do in that case. But especially if you're an engineer or chemist, you might want to begin that practice now because it'll help you along in the future. But I do it too, so, do as I say, not as I do. Josh? Because I can't use the 3 meter. I can't use a 3 meter because I don't know the speed at 3 meters. What you want to do is pick a position where you know the most information. And at the top, I know the position and I know the speed. I know everything there is about the object. Now, on every problem that you have, you'll have a position like this where you'll know everything there is to know about the object's energy. It'll usually be the initial position, like in that previous problem, because you know its height and you know its speed. Uh, Here, it's not the initial position. You don't know her speed at the bottom, but you do know her speed at the top. Is that clear? That's a good question. Juana? Sure, you could do that. You could also say, like Juana said, you could just say 3,000, that's her total energy, is equal to 1 half mv squared. And you would still get v is equal to, well, that would be 6 square root of 6,000 divided by 50, and that's also equal to 11. So yeah, you could do that for sure. Okay, and then finally, what is the woman's speed as she travels through the basketball hoop? So I say at the top, which is U1 plus K1, but K1 goes away because at the top her speed is 0, is equal to U3 plus K3. This is at the 3 meter point when she goes through the hoop. All right, I know the height So I know this value. I know her height initially. This was 6 meters, but I don't know the speed, which is wrapped up in this. So I only have one unknown, and I can solve this. You're not going to face any problems in this chapter with more than one unknown in the conservation of energy. So no substitution or any of that jazz. You'll have that on other problems. And later when we get into the next chapter, we'll deal with momentum and energy, and we will have some more complicated equations to solve. But in this case, I have one unknown. I have m times g. I'll go and put in the value here just so we can keep them separate. Equals m times g times 3 meters plus 1/2 mv squared. I cancel out all of my m's. I subtract this from both sides. So over here I get 6g minus 3g equals 1/2 v squared. And then I solve for v. So this is 3g times 2. The square root of that is equal to v. I subtracted this. I multiplied both sides by 2 to get rid of this. That's where this comes from. And then I took the square root of both sides to get rid of this. So the square root of 60, 7 point something. I don't know, what is that? What is the square root of 60? Frankie? 7.7. Alright, you will have a problem like that on the test for sure. It'll be framed as like a roller coaster or something like this. The one caveat that you'll have, and we'll get to that probably not today, probably next time, is that you'll have some non-conservative forces that'll be, say, a third part of that problem. But the first part of the problem will look just like this, where I ask you the speed at particular points, or I ask you the height at a particular point, assuming that you know the velocity at that point. Let's see, let's do, why don't you try this one, and then we'll do some more clicker questions on the concept test. We went to see A Midsummer Night's Dream this weekend. Was anybody working in that? I know none of you were in it, but anybody working in the play? No. It was really cool. Anybody see it? Wasn't it great? I thought it was really funny. About 15 more seconds, y'all. I'll stop at 225. 225. Go in here. let's see. I think D is right. I have a rock. It's thrown straight up. I want to know what is its maximum height. So I want to know what is H up here. Down at the bottom, it only has kinetic energy. Up at the top, it only has potential energy. I can set those equal. K is equal to U. That's 1/2 mv squared equals mgh. My masses cancel. I solve for h. It's the square root of 2gh. No, that's not right. Square root of v squared over 2g is the square root of 15 squared over 20. Is that 11.5? Is that right? Oh, yes. Thank you. Yeah, so I don't need the square root there. Sorry, I was getting carried away. It's just 15 squared over 20, which is going to be our 11.5. Okay? All right. Let's try a few more. We have some clicker questions in the back. I don't remember where we left off, but it was some past here, right? We did this one. I recall which one. Yeah, we did this one. Yes. We do this one yet? No. All right, let's pick up here then. Two stones, one twice the mass of the other. So one small stone, one big stone. What is the kinetic energy of the heavy stone compared to the light one? They drop to the ground. How do their kinetic energies compare? Grace, this is your example. All right, I'll stop at 55, 55. Okay, you'd think it was C, right? Because we've been talking about how the mass always cancels out. But if we're looking at the energy is just 1/2 mv squared, right? Because we're looking for the kinetic energy. Uh, and so because the mass of the bigger one is twice that of the smaller one, then it's going to have twice the mass. So actually the answer here is D. Don't be misled. When we're dealing with the conservation of energy, usually that mass does cancel out. And it doesn't affect the height or the speed, but it does impact the total amount of energy. All right? The difference is that the mass doesn't affect how the energy is interchanged between gravitational and kinetic energy. In the previous question, what is the final speed of the heavy stone compared to the light one? I'm going to stop at 30 seconds. 30. Okay, good. C is right. Are you excited? You drop them from the same point. Doesn't matter about their mass. They undergo the same acceleration, so they'll have the same speed when they get to the bottom. A child is on a skateboard is moving at 2 meters per second. A force acts on the child, and her speed is 3 meters per second. What can you say about the work done by the external force on the child? Has this external force done positive, negative, or zero work? I'm going to stop at 35, 35. Okay, awesome. Positive work is done. Work is change in kinetic energy or change in energy. So if I have an increase in energy, that means I've done positive work on this object. All right. My dad, he used to work for like the road department. Like they do road work, fix the roads and stuff like that. And my mom always thought that he was maybe stealing from the county where we lived. We call them counties in Mississippi. And one day we came home and all the signs were there. That was a joke. He didn't really work for the roads. He's a pretty honest guy as far as I know. He's a mechanic. He didn't work on the road. Okay, so a car starts from rest and accelerates to 30 miles an hour. Later, it gets on a highway and accelerates to 60. Which has taken more energy? The car going from 0 to 30 or the car going from 30 to 60? Or maybe both the same. All right, we'll stop at 45. All right, we're sort of, let's try this. I'm going to make a plot of kinetic energy versus V. If I make this plot, what's it going to look like? What shape is it going to be? What is the relationship between the kinetic energy and the speed? What type of relationship? Is it linear? Is it quadratic? What is it? It's a quadratic equation. K is 1 half mv squared. So K is proportional to v squared. So this graph, if I plot it, is going to be what type of shape? It's going to be a straight line. It's going to be what? It's going to be a parabola. So if I plot this, kinetic energy versus v, it's going to look like this. And that should tell you something about the energy required to go at different speeds. So let's try this again. Well, I want to know, does the most energy required to go from 0 to 30 or from 30 to 60? Which requires more energy? To go from 0 to 30 miles an hour or from 30 miles an hour to 60 miles an hour? Which requires more energy? I'll stop at 33, 33. Okay, that's a lot better. B is right. Um, in fact, that's why well, your cars are kind of a little more complicated because your cars are designed to get optimal gas mileage at a particular speed. I think it used to be like 45 miles an hour, but now it's probably, 90 miles an hour, whatever you'll drive. So, but if you go at speeds higher than that, then you're going to use more gas. Just because at higher speeds, the more energy that you use, then it takes more energy to go at higher speeds. So if I go from 0 to 30, say right here, I've just used this much energy. But if I go from 30 to 60, well, I've used this much energy, which is a lot more by a factor of 4, in fact. Is it possible for the kinetic energy of an object to be negative? I'll stop at 20. Okay, good. B is right. Kinetic energy is a scalar quantity. But gosh, you're thinking, we just did work, and you said that was a scalar quantity, but we can have negative values for work. Work is kind of an oddball. It's really the only scalar quantity we'll ever encounter that'll have a negative value. Remember, that negative value didn't give direction, it gave an idea about is it giving or taking away energy. But you can also think about kinetic energy as that 1/2 mv squared. So even if v did have a sign that was negative, it would go away. It doesn't actually because v is the speed, not the velocity. So it's not going to have a sign. All right, you and your friend solve a problem involving a skier going down a slope starting from rest. The two of you have chosen different levels for y equals 0. Which of your following quantities will your friend agree upon? They agree on his potential energy, his change in potential energy, or the skier's final kinetic energy. So we're almost out of time. I want to tell you the answer. The answer is B and C. We haven't really dealt with this very much because we're always taking our initial position to be y equals 0. But you can set your y equals 0 to be any position. I can have it be midway. I can be it at the top. And if you set it at any position, then the problem still works out the same, except you're not going to agree upon the absolute potential energy. Catherine? Yeah, so it's going to be E is the right answer. E. So y'all going to put E. Brennan? Because he asks, then how can we, if we can't have a consensus on potential energy, how can we have a consensus on the kinetic energy? Well, the kinetic energy is dependent upon the speed. It has a speed, and its speed is what it is, right? It doesn't depend how you observe it. It's still going to have the same speed, and same for the mass. All right? All right, guys, y'all have a great day. I will see you on Wednesday.